There we go. Now it's working. Okay. There we go. Okay, thank you for the raid toggle. So, let me finish the setup and then I'm gonna start. But to give an idea to everybody, I'm working on an OS from scratch, following a book, and I got out to the point of implementing kernel panic exceptions, and now I need to implement memory allocation. Write some filthy Rust. Okay, so what is the plan? The plan is to basically continue from where I left off. I will give you a brief introduction, like a brief overview of what I did before. Just let me, announce the stream everywhere. So let's go do that. Got Z questions? Come ask in chat. There we go. Okay, so this is done, and let me announce it on Discord. Other Discord. And let me also tell the people on Telegram. Okay. You know what though? Maybe one last thing. I should get myself a cup of tea. So I'm just gonna put it up. It's gonna be. I'm gonna put it up, then come back, explain what I did, get the cup, and then resume the work. That is the plan. Okay, so tea is warming up. It's in the microwave. It's not gonna take long. So long story short, what did we implement? We implemented actually not that much stuff. So we have, let's see, we have our kernel main function. Our kernel main function right now basically gets a bunch of addresses in memory that are defined by the linker. So like here we are like grabbing pointers basically from sections of memory from the linker where we decide to place stuff like where the kernel stack is going to be. Then we do some printing. Interestingly, like how do you print from the kernel? Well, the answer is that basically the QEMU machine that we're using has a BIOS that allows us to basically have access to some kind of console. And so printing is done through a syscall. So printing happens console is our like printer interface, and it has a write function. Think of it as the internal function that does the actual printing work that then gets utilized by the higher level like printer with with formatting and stuff that we normally use. And that one does the printing character by character by calling SBI with these parameters. SBI, it's a bunch of assembly. The book explains to you exactly what this assembly means and why things should be this way and not another way. So I'm not going to go through the full explanation, but that's pretty much all of it right now. And so the result is that, so our main does print hello kernel, and then it, I forget where we got back to. Oh yeah, and then it sets a function called kernel entry. What is kernel entry? Kernel entry here as the trap handler whenever like a CPU exception happens, like you divide by 0 or there's like an undefined instruction. And so we set that up so that we can handle those conditions from the CPU, and then we immediately issue a bad instruction. Unimp is like a bad instruction. And so this causes the CPU to complain that there's it has received a bad instruction, and that causes, and that basically that way we can test that we are actually calling our own kernel entry function. So which in turn it does a bunch of assembly to set up register management stuff, and then it calls into handle trap. And handle trap is this function that actually calls panic. What's interesting is that this thing calls Zig's panic function, because with Zig you can override the panic function behavior. So like if I in Zig I issue a divide by 0 by mistake, or like I do out of bound array access, then Zig in safe modes will have out of bounds checking, and it will produce a panic. And what's nice is that since we override the panic handler, the messaging, like we can basically hook correctly the panic message printing to the way we can print in the current context, which is not trivial. Like if your language doesn't allow you to override this stuff, then I guess I don't know what happens. Like your natural panics from like out of bounds access, that kind of stuff, either cannot panic nicely and will error out as it tries to panic, or all messaging gets disabled basically. So what's nice about this is that we basically can still maintain all the extra like tooling that the language has to help us understand when thing goes wrong. When something goes wrong. In any case, if you want to see this happen, piece by piece, so that you can follow along and understand what these things are supposed to be, go to the GitHub repo. In the README, there's a link to it, the VOD of the last session, so you can go watch that if you want. Okay, I'm gonna grab my cup of tea, and then we start checking out how memory application works. Let's go. Ragamat, hello, greetings from Brazil. Hello, hello. Okay, I'll be right back. There we go. Full setup. Okay. I maybe should show this actually running, shouldn't I? So we run Zig build run, that runs Q, that builds everything, runs QEMU, and we see hello kernel. So our main function print actually works. That print succeeds. And then we have panic unexpected trap. You know what? This should be kernel panic, I believe. Maybe. Let me think about it for a moment. The reason why I'm not sure if this should be kernel panic or not is because once we start having applications, I think this same mechanism would also handle issues with user-line applications, so user processes. So I'm not sure that this might print kernel panic when the panic is actually, well, not coming from the kernel. But you know what? We'll see once we get there. Okay. So also let me get YouTube chat enabled in case at some point somebody shows up from YouTube. Yesterday, a bunch of people showed up from YouTube. Usually, I don't really get many views from YouTube, but last time there were a bunch. So, in case they ever show up, we have them here. When are you going to port React Native to ChristOS? Good question. That should be the next thing on my list, right? Okay, so memory allocation. In this chapter, we'll implement a simple memory allocator, revisiting the linker script. Before implementing a memory allocator, let's define the memory regions to be managed by the allocator. Right. In a real OS, what probably should happen is that the system boots, the BIOS starts chatting with all the hardware, the BIOS collects information, including how many freaking memory sticks you have, and so then the OS, the kernel, then picks a region of memory to be that can be used by user programs, that can be used as like normal working memory. Some of it is reserved for the kernel itself, so that one is off limits for user-line programs. Like if you have, I don't know, 4 gigs of RAM and you have an OS running, obviously you can't use all 4 gigs for, you know, your random programs. Some of it has to be reserved for the OS. In any case, the point is that the size of that available memory will be based on what your system is capable of. Here is that we are like hard coding it, basically. The book probably will say that in a moment. Let's see. This adds 2 new symbols, free RAM, and this defines the memory area after the stack space. The size of this space, 64 megabyte, is arbitrary. It's an arbitrary value, and alignment 4K ensures that it's aligned to a 4K boundary, because we're gonna have to create 4K pages out of it and probably not have to deal with what do we do if it's not divisible. Like if you can't divide the thing by 4K, that would be a problem. Okay, by defining this in the linker script, instead of hardcoding addresses, the linker can determine the position to avoid overlapping with the kernel's static data. Yes. Practical operating systems on x86 64 determine available memory regions by obtaining information from hardware at boot time. I suspect this is not only x86 64, but sure. Yeah, that's what I was talking about. For example, UEFI's get memory map. Okay, let's go add that. Okay, so we align at 4K. We start with 3 RAM. We align up to 4K. 3 RAM, 64 megabytes, free RAM, and then we're gonna have to go in our Zig file and then get access to these things, which is gonna be kind of done like this. Let's see. Okay, so this is basically the equivalent of this line, what I just did. Then let's implement a function to allocate memory dynamically. Instead of allocating in bytes like malloc, it allocates in larger units called pages. One page is typically 4K. Okay, so this is like a hardcore bump allocator that just keeps bumping. And there's a static variable in here. Okay. So I guess there's a smaller question on whether we could come up with something clever ourselves in Zig using maybe one of the pre-made allocator functions. But the problem is that all the allocators that we have implemented in Zig, they're like fine-grained allocators. They're not like page allocators, understandably. So we have to implement a page allocate, like an allocator that deals in pages, I guess, no matter what. But I mean, this could still be a fixed buffer allocator at the end of the day, from our perspective. We make it a fixed buffer allocator, and then the point is just that we just ask it for k blocks at a time. You know what? So I understand why this code is implementing its own allocator. That it's funny. I get it. It makes sense. Uh, but you know what? We wouldn't gain anything from having a fixed buffer allocator at the end of the day. Let's do the work ourselves. It's going to be more explicit and fun, I guess. So function, what's it called? Alloc pages. So we need to have a slice that represents all these bytes. I'm actually curious if I can put this here. Can I do this? Okay, I'm not sure if this can be put in here or if it has to be put inside. So we'll see. Uh, yeah, but in any case, so this gives me a slice of all the available bytes. What we're missing is a variable that keeps track of how much memory we have already consumed. In this C code is this static variable. What's funny is that this static variable is basically it's a variable that survives calling this function. It's like a hidden global. It's a global variable, but its namespace inside. It's only accessible from inside this function. I mean, I get it to some degree, but also, what the fuck? See, for us, I think a normal global is going to be fine. Okay, so the code is going to be p other t is next p other plus equals n times page size. Right, so we need to create page size. They're not showing it. Page size is defined down here, 4096. So I guess we basically want to do this. We want to do result is gonna be pages from use mem last to pages times page size. Then we want to increment use mem. I guess we can do this const to alloc equals pages, or maybe let's call it alloc size so that we can reuse it. Okay, only thing that's missing is if use mem plus alloc size. Oh, it's the out of bounds error. You know what's funny is that check says if we go out of bound, panic out of memory. But what's funny is that we can kind of get the same for free from Zig as long as we don't do release fast. If we do a safe release mode, this is gonna panic for us. That said, it's only in non-release fast, so let's do the right thing also for release fast. So if this is greater than pages.len, um, panic. What did they write here? Just out of memory. Okay. Which is kind of brutal. In reality, you wouldn't want to do this. In reality, you would want to return a failure to the process and say, yeah, I can't allocate that memory and not crash everything. But bit by bit. Okay. So we have alloc pages. I think I've implemented everything correctly. Oh, we're missing the mem set. Okay, so we need to zero this stuff. It wants us to zero memory before we return it. Fine. There we go. Okay, let's make this work then. Let's see, isn't it simple? However, there's a big problem with this memory allocation algorithm. Yeah, it doesn't free shit. Yeah, of course. It's fine. Okay, let's try memory allocation. Let's test the memory allocation function with, by the way, for us, making this work, it's trivial, like in a more serious fashion. Maybe not the optimal way, but in a more serious way to make it work. All we need to do is wrap this array in a uh, fixed buffer allocator, and then build a general purpose allocator on top of that. So by building a general purpose allocator on top of it, we then have actual like tracking of memory allocations and freeing and stuff. Would that be optional or would that be optimal? Probably not, because GPA is for variable size allocations. In our case, well, technically in our case, they also are variable size because we're dealing with pages, but I think you can unmap individual pages. So it's a slightly different semantic than what normal allocation looks like. But in any case, let's test this stuff. So how do we make this work? Hey, Jimmy Zippo came from Toggle. Hello. Wait, are you like Toggle's kid? I'm joking. So this calls the function tries to alloc pages. That's not the greatest test, I guess. But okay. Okay, let's make this happen then. In kernel main, then what do we do? Okay, so instead of we do set stvec, I think we want to keep that one. We do want to keep hello world. We don't want to trigger unimp anymore. We leave it commented out. Maybe we can even do it like this to show people that these things are correlated. And then on here, we try to do the two allocations. Uh, Maybe we can do X for the pointer and then length. The problem with the slice is that I don't think we have a way of saying, yeah, can you print these slices just the pointer and the length? Which is unfortunate. Okay, hello kernel, and then unexpected drop. That is not good. What's going on? Oh, there we go. Okay. I think I was in the wrong directory. Yeah. Let me close this then in case so that I don't get tripped. I recently started using aerospace as well. Working a table-based way, so Arc fits in nicely. Yeah, I think that like Arc is nice, but I don't know if you heard that they're like abandoning it. It's kind of disappointing. Like the startup that made Arc, so that Arc with its current design isn't really, becoming groundbreaking. Like it's not having an exponential adoption curve. So they decided to abandon it in favor of a new project, basically. Well, they're saying that they're going to maintain it. They're kind of going to feature freeze it, basically. Yeah, that's the problem with this type of companies that make stuff and then they get venture capital. And if they don't hit the hockey stick, then, you know, they throw everything away. There was a funny YouTube short on that regard about a guy that like got his conscience uploaded in a kind of virtual reality thing, but then the startup pivoted to something else, and like his consciousness is now in that thing where like he was promised features like some kind of basically virtual paradise for his digital conscience, and now they're not going to make it anymore, and now they're pivoting to some kind of like business as a like B2B company. Like uh it was really funny. Let me see if I can find it. I actually don't know. Okay, so if anybody knows what I'm referring to and wants to link it, I would love to watch it on stream. Otherwise, I'm not gonna search for it. I think I'm not gonna be able to. Okay, let's fix our errors. Error union is ignored. Right. Oh, you know what we can do? Here's what we can do. Kernel main. Let's do it like this. Calls main catch calls main, and then how do we panic on an error? Let's see, catch or you're talking about the series upload. I think it was a short video. So not necessarily a short as in vertical. I did see it in YouTube shorts, but it was I think it was a like a short video made by a YouTube channel, not exactly like a TV series. Ghosty? Ghosty doesn't have link detection, does it? Let me see. Okay, so That one, wait, okay, so this one is, yes, this is the annoying video where the CEO of Arc is saying that they're basically abandoning the project, but that you should still be happy about it in favor of something else. It's not the funniest skit, but yeah, it's related. So if you want to see the announcement that Arc is dying, it's this one. I should have done this earlier. So, okay, what is this changing? Basically, the outer function has to be a C function because it needs to be called by a bunch of C like stuff. But inside of it, we can call a Zig function and catch errors from it, and that allows us to have our like function with all the business logic. We are allowed now to have like an error signature, and now we don't need to do catch anymore, like catch nothing. We can just do try, which is so much nicer. It's more idiomatic. And we can use try because try will bubble up the error, but then we catch it here. And then like this is where basically this way the the seam, the point where we connect the quote unquote Zig ABI to the C ABI, it's like just one point instead of being like a bigger surface. And that way, yeah, we can use try. Does this make you happy now? Function declare no return implicitly returns. Yeah, you are right. You know what? We put the while true in here then. Tab U size does not support field access. Oh, where do I do .lan? Pages.lan. I'm doing something dumb. I'm definitely doing something dumb. That is ram.lan. Also, oh my god, what was I doing? It's ram that needs to be sliced. Yeah. Label run. Unable to evaluate compile expression. Yeah, so it turns out, oh what? Not even that? So we can't even do int from pointer outside. Okay, I thought this would be allowed, but I guess we can't do anything on the outside, which probably means that this needs to be in here. Invalid string formatting for type pointer U8. Oh, where am I doing this? So I did create this printing here, but this seems fine. I did do this printing here. This is probably the SAS one. Although this is len, should be fine. The problem is, unfortunately, is that Zig is not good at telling you where you fucked up with FMT. Invalid format string X for type pointer to U8. Oh, wait, isn't X fine for a pointer? I guess we want this. There we go. Hello, kernel. And then there's 1 and there is 2. What do you know? One is 1,000, the other one is at 2,000. And that is correct because for kilobytes, it's 1,000 in hex. So success. Verify that the first address, p address 0, matches the address of free RAM. Yeah, okay. How do we check if this matches the address of free RAM? We need to do LVM. I don't remember what nm does. Oh yeah, it's nm that we care about. RAM. Wait, there's no RAM definition in here. Wait a second. Am I doing something dumb? I don't remember what an M does. An M should tell you about symbols, right? Is it not called? Is this stuff not called free RAM? Yeah, it is called free RAM. Oh no, I know what the problem is. I did Zig build run, but Zig build run doesn't install the updated executable. Okay, so in any case, free RAM starts at this address, and that is where the first allocation is. So we're golden. You know what? I don't know why I didn't do this in the beginning, but here's what I'm gonna do. I'm gonna say that if you call run, uh, run should also depend on calling run should also install everything. So the calling Zig build run will also install the artifact. Maybe that's not always appropriate, but it feels appropriate in this case, since I need to have like easy access to the kernel image so that I can run other tooling on it. Okay, process. So that was easy, although we didn't do much system integration, right? We just created something that kind of gives us pages. Fine. This is where the meat starts, I think. A process is an instance of an application. Each process has its own independent execution context and resources, such as virtual address space. Practical operating systems provide the execution context as a separate concept called a thread. Yeah, we don't have threads, I'm guessing here, but yeah, so one process, one thread. Should it be public for that? No, it doesn't need to, because we are not grabbing this variable. We're grabbing definitions from inside the linker script. Let's see. Prox max 8, prox unused 0, proc runnable process, PID state, SP stack. Oh, we are like inlining the stack inside the process struct. That is hardcore. Okay, that's fine. I guess we're gonna need to implement this stuff ourselves, but we're gonna do it in a Zig way. So I think we can do better. So here's the memory stuff here. Let's put here the process stuff. So const process. Okay, what did we say? It has process ID, state. We're gonna make. Okay, let's make this stuff nice. So ID, usize, state. It's an enum. What do we say is unused runnable. Unused. What does unused mean? Oh, you know why? It's because it's creating an array of these guys, and so unused, it tells you that it's like a free slot in the array, right? Where is it? Where's the array of these things? Yeah. Okay, these C-isms I don't love. So what we could do is make an array of optional processes. PSA switch to trailer out. Okay, if it's short and you have a link, I'll check it out. I want to see the real switch too after all the rumors. A process should still have a state though. Like it needs to have like running or not running or something. I don't know. Necrophaeus, hello, I'm new to Zig, started learning it because of your interview on Developer Voices. Nice. And I want to learn it by doing some GPU stuff, also learning that. Any suggestions? Maybe you can do the ray tracer in a weekend stuff, but in Zig. I'm sure that plenty of people have already done that. So you will have to do the work. I believe that the original book uses either C or C++. So you will have to translate that to equivalent in Zig. Most of the time, it will be trivial. Maybe not always. When it is not trivial, you can reference, versions that have already been made in Zig, or you can ask around for help. And I think that should be nice. Like with this book, for example, I am translating like the book for that tells you how to create an OS in 1,000 lines of code uses C, and I'm translating that to Zig um, myself. It's mostly easy, not always trivial. So yeah. Alternatively, I don't know. You could try to create one of the classics like a Tetris game. You can recreate a Tetris game, see how far you get, ask around for help. The Zig Discord community has a bunch of active people that also do this kind of stuff. There's also existing implementations of Tetris in Zig, like graphical Tetris. So, you could look at those for inspiration. But I think what's nice about, Ray Tracer in a weekend is that the book guides you step by step. So, like, that's easier. Maybe you can start with something that guides you step by step and then leave something more freestyle as a second project. But I guess it's up to you depending on your sensibilities. Okay. 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 Huh. Okay. 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 Hey, ending with Ali. Thank you for the raid. Hello, everybody. Yeah, this is totally a OS from scratch programming stream, day 2. I was just watching. I was just watching the Switch 2 announcement trailer. It's okay. It's okay. Yo, these triggers, intriguing. I think so. I would have to touch it to really know, but I feel like that it seems that the effort that they put in improving the ergonomics and like refining the original concept is probably an improvement. Like it's gonna make a difference. It seems I'm sold. I'm sold on the idea. Will I buy one? I don't know. I bought the Switch, the original Switch, pretty much for 2 reasons: Zelda and Super Mario Maker. So, and then lately I'm not playing any of these things anymore. Uh, so they need to make a new interesting Zelda game for me, basically, or a new Mario Maker for me to buy this device. But it seems cool. Good job, Nintendo. So, okay, hello everybody. Welcome to a actual OS from scratch stream. Not joking. We are implementing user processes. So you're actually joining at an interesting moment. I'll buy it for a Metroid game. You know what? That is a good point. I forgot about it, but I did enjoy Metroid Dread a lot. It was nice. I'm not a huge Metroid fan, but I did like Metroid Dread. I don't know if a new one would convince me to buy it. And if I have to be honest, the Zelda game would have to be different than Breath of the Wild. I liked Breath of the Wild. It was fine. I enjoyed it. The one after, Tears of the Kingdom, I didn't play because I was kind of done. I watched the gameplay online, but like I watched a playthrough, but I don't know, the story was boring, didn't make much sense to me, and I wasn't super interested. And like I get it that you mess around with the crafting, and the crafting is cool, but I don't know. I played Zelda games 50% for the kinesthetics, 50% for the story. And I felt like the new one didn't really have enough story juice to convince me. Um, but we'll see. Powerful enough that it's invisible to emulate for many years. Yeah, I think usually when a new Switch comes out, it's usually like given the delay that it, like the time that it takes them to uh, design everything. Usually, it's like using not the latest generation of hardware. So, but I think it's actually fine. Honestly, I like if you think about it, maybe in the past, actually, definitely in the past, the power of a console made a difference. But nowadays, to me, it seems more of a like a honeypot more than anything else. Because games are look decent enough already, more than decent enough. And most of the time they invest a ton in graphics and then they don't invest enough in gameplay, fixing bugs like Q&A and a compelling story. And I think that Nintendo historically has been a good platform because game developers spend effort in creating compelling narratives and compelling gameplay out of fewer moving pieces. Like, okay, let's say that the Switch 2 can't run Call of Duty. Fine, Call of Duty is trash nowadays. Anyway, it's like it's heavy, buggy, boring, soulless. So even if the Switch can only play like simpler games, like less demanding ones, I think it's fine. Okay, so I'm not sure what we're gonna put in state. Should we do the? Okay, you know what? Let's emulate the original code maybe because we can. So we can make these things optional. Although, no, you know what the problem is? The problem is that they are basically making this thing a. They're making the array. Let's follow the original design. It's not gonna be great, but let's just follow it. It's fine. So let's say, what is it? Unused and runnable. Then what else do we have? The other TSP stack pointer. Did we define a the other T anywhere? Did we at some point define that thing? Because I think it's a type of data that I probably skipped myself. But in any case, it's a U size. And then kernel stack. I'm confused why this is called kernel stack, but it's inside a process. It's the stack that we use as the kernel to handle syscalls for this process. Is that what it is? I'm confused. I'm confused by this comment. Okay, well, let's follow along in the meantime. A thread has both a user space and a kernel space. No, kernel space stack. No, I don't know. If you had asked me before I saw this, I'm okay. I'm guessing you decide how you want to design your system, right? So you choose. But the kernel 100% has its own stack in separate memory, and you can see that in the linker script. In the linker script, this stack here of 128 kilobytes, this guy is our main kernel stack. Like this is what we are currently using right now to run this function, and call these printing functions. So the fact that there should be any kernel related stack memory that is attached to an individual process, I guess it has to do unless that comment is wrong. By the way, there might be just a mistake in the code snippet, but if that comment is right, what I would expect is that it's used when calling into the kernel from user space. Maybe you usually have an additional kernel stack for each user space thread. Okay, so it seems that people are saying that this is a common thing to do, I guess. Let's see. The kernel stack contains saved CPU registers, return addresses, and local variables. By preparing a kernel stack for each process, we can. By the way, we could have just read. You know what? I was making fun of Togglebit for not reading the freaking book before jumping to conclusions, and now I'm doing the exact same thing. By preparing a kernel stack for each process, we can implement context switching by saving and restoring CPU registers and switching the stack pointer. Tip: there's another approach called singular kernel stack, so apparently you don't have to. Instead of having a kernel stack for each process or thread, there's only a single stack per CPU. Cell4 adopts this method. This where to store the program's context issue is also a topic discussed in async runtimes of programming languages like Go and Rust. Try searching for stackless async if you're interested. Okay, context switch. Switching the process execution context is called context switching. The following switch context function is the implementation of context switching. So let's see. Save the callee saved registers onto the current process stack. Add immediate to stack pointer. Space for 13 times. Oh, they now flip this around. Previously it was -4 times 13. So 13 things go onto the stack. Switch the stack pointer. Restore callee saved registers from the next process stack. Right. So the way this works then is that we are passing as an argument the new. Okay, yeah, we're passing previous and next. Previous to stack pointer. I guess it could be, we could call it maybe current, although current might be wrong because currently we're actually in the kernel. So previous stack pointer is the first argument. Second new stack pointer is the new one. Okay. Switch context saves the callee saved registers onto the stack, switches the stack pointer, and then restores the callee saved registers from the stack. In other words, the execution context is stored as temporary local variables on the stack. Alternatively, you can save the context in the struct process. But this stack-based approach is beautifully simple, isn't it? It is, but this only works for cooperative scheduling, right? Because you're kind of making it look like a function call from the perspective of the process. Okay, let's implement this stuff and then we can continue reading. So it kind of is going to look like some of what we already did. So let me copy maybe kernel entry, or at least some of it. And I'm going to put it, where should I put it actually? Well, I guess we can put that in the process, right? That would make sense. Okay, so first of all, make space for 13 items. Then we store words RA and all the S's. We're not storing the other ones because the other ones we don't have to store. Then switch the stack pointer. Store word, store A0. No, store SP at the pointer of A0, load. Okay. Restore colli saved registers. Yeah, basically we do the inverse of this, but now we have a new SP. So I think we can do this. And they switched they from the previous examples they switched around these numbers. I mean, it's multiplication, so it's fine. Just funny. Okay, so we should have done everything correctly, and then what do? We right, we pop from the stack, and then we read. Okay, so we read. That is returning from a function call. Okay, let's see how this is going to be used. I think this approach is like leveraging a bunch of assumptions that are not being told to us explicitly to make it work more simply. Why 18 SP? Shouldn't there be 1 SP? Do I have 18 SP anywhere? Oh, this. Oh shit, you're right. It's because the original code had like more stuff. No, the original code had more stuff. Thank you for catching this. So I guess I'm gonna copy again and change it again. Okay. So blah blah blah. Let's see. Switch context saves the callee saved registers onto the stack, switches the stack. Okay, I read this one already. Callee saved registers are registers that a called function must restore before returning. In RISC-V, S0 to S11 are callee saved registers. Other registers like A0 are caller saved registers and are already saved on the stack by the caller. This is why switch context handles only part of registers. Yeah, this is the thing. Like this only works because basically our code will explicitly trigger a context switch. Like the user process is expected to trigger a context switch, which in turn means that the compiler, since we're calling this function, the compiler will also assume that as we return from the context switch function, it expects also those registers to now be potentially scrambled. While if we were implementing preemptive like context switching, then it wouldn't work this way because we would probably also have to save also all the other registers and then restore them again back. The naked attribute tells the compiler to not generate any other code than inline assembly. It should work without this attribute, but it's good practice to avoid unintended behavior. We don't need a line 4, I think. Okay, wait a second. What am I modifying? I need to rename this, right? Qualcomm is still naked. We don't need the alignment. Is this switch context perhaps only for in kernel mode context switching? Probably we're going to start with that. But I think later on we're going to switch to user mode. But I guess it's like 3 chapters afterwards. So yes, it's going to be a while before we get there. Okay, let's see. Next, let's implement the process initialization function create process. It takes the entry point as a parameter and returns a pointer to the created process struct. Find an unused process control structure. Okay. Maybe I should even call this one. Does this one? Yeah, this one needs to be naked and like weird, but create process can be like a normal function. So program counter usize returns a optional. Well, I guess this one is panicking if it fails, so let's make it panicky as well. Process, totally different thing. So we need to have an array of processes, right? Yeah. Hmm. I think I can do this. Is this zeros or zero is? Zero is. Although that is not default initialization, right? This is like forced zero, which is not what we want. We want default initialization. So how do we do this? I guess we do procs equals array underscore proc process. Eight times this. For Zig, what is the best one stop reference for patterns? I don't know, man. I would say that question sounds sus to me. You probably want to find places where you can find like I get it. Like the question is, how do you do things in an idiomatic way? And patterns are a way of doing things idiomatically. But I would say probably the best place where you can see patterns, but they're not gonna be laid out to you in like in a asectic setting where there's the pattern dissected explicitly, where you can observe patterns being used in real life. It's the Zig standard library, and maybe looking at other popular projects. That's the best way. But nobody will tell you that something is a pattern. Like you will recognize it by seeing the same thing being done multiple times by multiple people to achieve a given outcome. And I think learning patterns in this organic way is the right way of doing it. If you expect to find if somebody ever tries to make a Gango 4 book for Zig, yeah, no, I would recommend strongly against consulting that type of source material, because without the context around a pattern, you don't really learn what the pattern is really for. And case in point, Gango 4 patterns are abused to hell and back. So here's a pattern for you, for example. I need to find a available slot inside this procs array. Here's what I do. I use a for And in my for, I grab a each individual p as a process. Probably I want it to be a pointer, and then what I do from there is I check if it's unused, right? So if p.state unused, then I break the for loop with p. Else, if the for loop doesn't find anything, I panic. And what's nice about this pattern is that basically I'm using a for loop. By using a for loop with break and an else branch, you can give an else branch to a for loop in Zig. I'm using the for loop as a like a search thing. I'm searching, and if I'm not, and basically the else triggers if the for loop ends without breaking. If we do break out of the for loop, we don't go into the else branch. That's the idea. Okay, so now we have P. What do we do? Oh my god, C, why are you like this? Stack coalesced registers. These register values will be restored in the first context switch in switch context. So, hello Dan. Welcome to SDev. Thank you. I'm just a tourist though. I'll be straight with you. I'm reading this book and doing the bare minimum work to implement the basics because I'm writing a book, a Zig book where I want to, tell people about syscalls and stuff. And I studied some of this stuff in university, but I never really got my hands dirty much. So I'm doing it now, but like I'm not attempting to make a real OS. I want to get to the point where I have user mode, system calls, and that's where I stop. Like I don't care about the file system. I just want to basically have enough OS to be able to run a user mode hello world on it, and that's it. Okay. And what's funny is that I was saying this in the past, but I'm I don't know, not really happy, but like I'm amazed at how right I was in saying that every single type of material that uses C to teach you stuff, it's riddled with fucking C isms everywhere. C isms that you don't need. Like, what is this shit? Well, this is nothing. It's like previously, like there was a previous point where it was trying to teach you how to implement print because you need to implement a basic print that you can print with the help of the BIOS and like it's teaching you about VA stuff because print is variadic. It's like my god, what is this garbage? You don't need to learn this trash. Anyway, process. Okay, so we're accessing the stack field. The stack field in our process struct is it's an array of fixed size, but I believe this turns into a pointer, right? The actual struct will contain a pointer basically to the beginning of that memory. Like everything else gets forgotten. So we're accessing this, and we're accessing size of proc stack. So we're pointing at the end. So this gives us a pointer to the end of the stack. And then we're zeroing that memory as we decrement the stack pointer. The last thing that we put in there is the program counter. We set the rest of the things, and then we store the stack pointer. We save it in SP. After doing this procedure, and then we return. Okay. Is there a better way of doing this? I don't know. I guess we can do basically, we can slice the stack at size of this thing, and then instead go forwards and not go insane. I think that's what I'm gonna do. So I'll do this const sp is I mean, I get it. Like, what you gain is that you need other variables. Like going forwards, like going imperatively backwards helps. If we had Zig 014, we could actually do this math. Like we could implement this also in Zig directly without without needing extra machinery. But with 013 is a bit annoying. Honestly, what I'm thinking is that this should be a struct. Like there should be a struct that describes these registers, and we just we do like we cast it as bytes and we just put it there. Blop. With Zig, you can do pointer arithmetic without first turning the pointer into an integer. Well, okay. Let's do it like this. SP is int from pointer of p dot stack pointer of p dot stack plus, or I guess we could do pointer of last element of stack. That also would work, right? Um, it's unfortunate because we can't do easily size of. I think we can repeat the number though. I guess. So this is the pointer of the last element. And then this is not going to be as nice, but we can do sp dot star equals 0, right? A bunch of times, 13 times. Need to typecast to a U32. You are indeed right. It is annoying, isn't it? Okay, you know what? Let's do it in a different way then. Let's do the cast first. Let's do the typecast first. Although this is not going to be SP anymore. Maybe let's transmute the entire stack. I can turn the entire stack and then slice it and then fill it with a for loop. That's probably the best idea. It's was it bytes to value? Is that it? Given a pointer to an array of bytes returns a value of the specified type. No. Baked by a copy of those bytes. No. I guess we can just do a pointer cast, can we not? I'm curious to see what the compile error is going to be for this. Why for what I just did. In any case, more or less we should be there. And then for regs, starting from where? Regs.len minus 13, right? Let's do 12. Then here we're doing basically the zero stuff. Hmm. Yeah, okay. I think it should be like this, right? We turn our array of bytes in an array of U32s. I will probably need to add more stuff in here, but this should roughly work. Usize stack. You're right. It's the same thing though. Usize U32. So it's an array of registers now. Then we do at minus 13. That's where going to be our stack pointer. We place the program counter there, and then all the next ones, all the ones that are remaining, we zero out, which is actually not even that important, I think, but we do it. And then we can do a return. Actually, before we do return, we need to set more stuff, right? p.pid equals something. What do they do in here? I plus 1. Oh, right, because they remember also the increment variable. I guess we can do this. It's kind of dumb because this should be initialized in the beginning, I think. Oh, well. We don't set the PID. What else do we set? State, we've set it to runnable and set DSP. Okay, there's going to be a bunch of programming of compile errors that we need to go through first. Let's go do that. Or not? Are you shitting me? There is no way. Oh, you know why? Because this is not referenced anywhere. That's why it's. I'm not using it, so this is not getting type checked. I thought it was starting in a 32-bit machine. Why is the stack pointer usize and not U32? Because usize on a 32-bit machine is a U32 basically. Usize means the natural like word size of a given machine. So saying usize, like it's worth using usize in your programs normally when you're defining, for example, the type of a number that is an index of an array, because on a 32-bit machine you will be able to do 32-bit like an array can be up to 32, can have up to 32-bit worth of values, while a 64-bit machine will be able to have more, right? So you write usize and it like automatically like specializes depending on the machine. In this case, usize and U32 are like literally equivalent because I'm only targeting one machine. Like it's very machine specific. Okay, testing context switch. Let's see, testing context switch. How does it work? Let's see what happens in main. So we create two processes, and then we launch the first process. The first process prints A, forever prints A, switches context that sends us to that causes us to run proc B entry because proc B will be set to have the program counter set to start from the first instruction in this function, that's going to print B and then switch context again. So we go in here. Well, we kind of go in here by quote unquote returning from this function. We're not really returning from this function for real, but it's going to look kind of the same. And then yeah, because actually the return from this function puts us in here, because when ret gets executed in here, we find ourselves in here because the program counter will have been messed with in the meantime. So it's kind of funky, but it works out. Okay, let's do this and see how that works. Where is it? Process A. Delay is also to reduce the amount of spam, I guess. What does delay do? Not being hardcore. Okay. Holy shit. How many times did they do that? Jesus Christ, a bunch. Okay, copy. 30 million times. Okay. And then process B is the same. Context switch needs stuff though, right? Oh, proc A and proc B are global variables. That's how that works. I mean, we have this algorithm for finding a slot where to put processes, and then we where code this stuff. I feel like we are doing a little too many back and forths for no reason, but okay. So var PA pointer to process. PB. We need to set these things afterwards when we define this stuff, when we actually create these processes. So context switch will go from PA to PB, and this will say go from PB to PA. But more importantly, switch context doesn't take a process. It takes only the stack pointer. Context switch. Oh shit. Wait a second though, but I have to define context switch as a function that accepts arguments, right? Yeah, I forgot about this. And I don't use these names because I'm using A0 and A1 basically. Like A0 and A1 are the registers where the arguments go. So like it's kind of the same thing, but it's weird that all these things are like, all these pieces are like not wired together, and it's dumb. What am I going to call this? Curve pointer to U32. Yeah. Yeah, they're unused. But I think I can do this. This would be, I think, like this. I don't know why I'm embarking in this adventure because it was actually working as it was before. I think. We'll see. It should work. Okay, basically this is saying, again, A0 and A1 are the registers where this value and this value go. But now I'm more, I don't know, quote unquote, correctly wiring the function arguments into the assembly more explicitly, I guess. There's gonna be some more type errors that we need to fix because, like, this is the stack pointers. How did I define the stack pointer as a U size? No, it's a pointer to U size. And I identify these things as pointer to U32s. God damn it. There you go. Okay, so now in process A and process B, am I calling these things correctly? I am almost. Okay. Now I need to create the processes, call the first process, and set the global variables. Okay. Okay, so we allocate two pages. Well, I guess we can leave that there. Maybe we can put this into another set of curlies so that it's clear that these things are like, it's another thingy. Functions are called process A and process B. Okay. And then we call process A. Okay, let's watch the compile errors fly in. Error union is ignored. Console print. Right. Catch do nothing. Next. Unable to call a function with naked calling convention. Ah, that is interesting. That is really interesting. In C, apparently you can put this here and it works. In Zig, we're getting an error. Unable to call a function with naked calling convention. The original text was saying that it doesn't need to be naked, that we can remove naked. You know what? I will remove the naked calling convention thing because I don't think it's needed. I guess we can look maybe later at the disassembly and see what ends up being in there. Okay, let's see. Next. Except the type usize found a function. Right. So this needs to be, I guess, a pointer to. And then the signature here is that that's a pointer to. Hmm. Can I do it like this? Except a pointer to any opaque found pointer to const call conv void. Okay. Well, you know what? Wait, can this work then? Oh yeah, this course is nice. Okay, so this is what I want. SP register memory should point to the clobbers. Oh shit, you're right. What about clobbers? Guess what? They don't have any clobber. No, the SP register memory should not go into the clobber. No, okay, so here's why I think it's fine that we don't have those. Yes, some memory is touched, but it's a different process. And in theory, the other process, we haven't implemented it fully yet, right? But in a full-fledged solution, you like these are different processes, so there is no memory that one can observe that the other could touch. Unless we start implementing, ways of for processes to share memory, but we're not gonna do that. So um so that should be fine. As for the SP register, no, I think that putting the saying that the SP register has been clobbered um, shouldn't be the case because we're setting it like we are setting it like we want to override it, and the value that ends up being there is going to be the original one. So we haven't clobbered it. Yeah. Okay, but I'm having type troubles. Let's see more type troubles. Let's see expected type pointer to size found comp time int. Right. There you go. Undefined. Next. Pointer capture of non-pointer type 8 kernel process. Right. No field name PID in process. Oh. To do, implement pointer cast between slices changing length. God damn it, man. Really? I hit A to do? Oh my god. I hit A to do in pointer cast. Okay, so yeah, I was getting. I'm not even sure this should work as is because I'm doing a bunch of stuff. I'm casting a pointer, and then I'm also turning it into a slice, and then I'm changing the type. So I'm doing a lot of work in here. Let me think how we can do this. I mean, I know what I want to do. I'm just thinking what is the least annoying way of doing it. Probably it's this. We open a block and we do all the weird surgery in there. I think this math surgery is annoying. Let's see. Pointer cast increases pointer alignment. Uh, yeah, align cast it. Although it is true that the alignment is not necessarily going to be good for us. How do we? Oh, it should be fine. Excited type use size phone pointer to constant pick. Blah blah blah. Okay. We got something, but we didn't get what we wanted. Because so there's a bug because so here's what's happening. We are running, we are invoking we are correctly entering the we are creating processes, then we are correctly entering process A. Process A prints, but then it tries to context switch, and that goes poorly. That does not go well. Let's try to print the. Uh, I'm gonna try to have it print the stack pointer there. But I want to know so this is going to be the stack pointer. That seems, I don't know, roughly reasonable. What I care about at the stack pointer though is that it should contain the program counter, right? At minus 13, that's where we put the program counter. I probably have an off by one error of something or something of that sort in my things. Also, this is going up to 12. I have a problem with this. Okay, I'll revisit this in a moment. Let me print stack pointer to star. Can I do that? Is that the correct type? It is. Um, I think I want that in hex. $178. Oh god, there's a bunch of stuff. Okay. Okay, process B, the label process B starts at 00178. So we are correctly storing the program counter, so the instruction of the function where we need to go. We're correctly storing it in there. So this value is correct. So maybe we do something wrong in context switch. Maybe the surgery that I made is wrong. Doesn't it need to be naked? We could make it naked. The problem is that then the type system wouldn't make it work well for us because we want to pass it arguments and then we need to specify arguments. Um, Also, yeah, what's in, I guess, what's in that function? Is there a flag for object dump that where I can ask for a specific symbol or I guess label or something? Let's for disassemble. Disassemble symbols. List of symbols to disassemble. Okay. Is there any other short version for it? Like D? No. Okay. No, we want context switch. In the end, context switch contains. Yeah, this is just like, it just happens that it has an extra red function at the end that does nothing. Like there's like basically there's like a little bit of trailing trash that does nothing. What does it mean to be naked? That it does not push its return address and stuff? Um Good question. In this case, the difference between naked and not naked is the red function. One red function, sorry, instruction. One red instruction is in here because it was in our assembly. Like we in our ASM, we do end with a red. Also, let me see if it's correctly doing. Yeah, it's correctly picking up that these arguments end up going in A0 and A1. So this is also correct. Like everything is correct in here. Everything seems correct. I still suspect that I might have an off by 1 error in any case and somewhere, if I have to be honest. But it seems fine. So basically, this is doing 13 assignments, right? No, because this is +1. I think this needs to be like this. Because len is +1. Well, whatever it is, this has changed nothing, to be honest. So nothing has changed, actually. Oh, you know what? Wait, here's what we should ask ourselves. Where the heck are we now? Info registers. Okay, so what are we doing right now? Where's our program counter? Program counter? I forget. What's the program counter? Isn't PC the program counter? Oh, it's up here. Okay. 220. Ah, fuck, I need more context in the bigger window. Okay, is there a object dump, but give me whatever symbol is around that address? The symbol options. Okay, so here's what we do then. We pipe in less and then we search for 220. Program counter is kernel entry? No. Why is it kernel entry? Is it trying to trap? Yeah, so kernel entry is because it's trapping. So I think there's something that went wrong. But I don't understand why it stops in here though. Why is it not moving forward from here though? Man, try to do something without Jacob-Lee. Things get funky very fast, huh? Okay, I think the problem is that we're probably. I feel like we are fucking up the glue code between some of these things. I feel like the context switch doesn't do the right thing. I don't think your SP is initialized correctly. Hmm. Print out the SP. Okay, so to understand if the SP makes sense, the SP needs to be. Well, I mean, but the SP is not a problematic part, is it? By itself. Like, okay, if by SP we're referring to the SP field inside of a process, if we're referring to that, then we do set the SP correctly to the pointer to the location in our kernel stack, in our per process kernel stack, where we're going to put the program counter. And that is correct. We know that it is correct. You know what? At the release for for process B, because for process B, when we look at this, we see that this correctly points, like the thing at the bottom of the stack pointer is the program counter to the next function, and that is correctly set uh, to the process B. Where is it? Oh god, I had it at some point. That is correctly set to process B, right? 178, 178. But the SP in your registers doesn't look good. Right. Let's see. So the stack pointer in my registers is this guy. A non-naked function restores shit. So that's the problem you're saying. But why did we not see that? Like in looking at the disassembly of context switch, it looks like it's only doing what we tell it to do. Subtract from the stack pointer, put values in it. As the last thing. Oh, you know what? It's probably wrong. Oh, you know what? I think I misunderstood how this relates to the other code. Maybe. Because wait, so this code is what is it? It's subtracting 13 from the stack pointer. And then it's slowly going up. Wait, isn't this wrong? So this is storing word. This is storing the contents of array at 0 times 4 at SP. And then we're overriding that. No, wait, this is the opposite. What am I doing? This is saying I think I'm misunderstanding what that code does. And I think I made wrong assumptions about things somehow. Okay, let's go again through what this does. So switch context makes space for 13 variables, well, registers, whatever, words, and saves each one of those at a different location. Different offsets based on stack pointer. And so that fills 13 slots. Where the final one, this guy, fills the very top of the stack. Like this is the very end of our array of bytes. Then this writes at the location pointed to the first argument the current stack pointer. And then loads from A1 and then puts A1 as our new stack pointer. I'm probably not doing this correctly, I'm guessing. Oh god, what did I do? I did a bad click and Ghosty died. Holy shit. Oh my god. Oh, I never saved the contents. Man, Ghosty really did not like that click, huh? Okay. So what was I saying? So we were looking at what this code does. So this saves. So SP. I guess the question is, what is our current SP? Our current SP. Oh, you know what the problem is? Probably, I think that our current SP, like, okay, so what is our current value? Maybe this is what people were saying in chat earlier. What is our current SP at this point? Isn't 178 the program counter, not the stack? Yeah, but the stack at that address should contain the program counter, and it does contain the program counter correctly, because that's the what's it called? Isn't that what we're supposed to put there? I believe so. Like the process initialization puts the program counter at the end in there. So yeah, I've been following along but not fully understanding what this thing is supposed to do. Like I had a vague idea but not precise enough. So switch context gets called as we are running a process, right? So let's look at let's look at this. Like we call process A from here. To be fair, when we call process A from here, oh wait, do process A and process B also have a naked calling convention or something like that of that sort? No, they're just normal functions. The thing is, when we call proc A entry in here, our current stack, is the kernel stack, right? Our stack pointer, our SP points to the kernel, like the SP register. So we enter entry, and then we call this. What does switch context do? Switch context manipulates the SP register. No, I think the problem is that I feel like the problem is more with the book than what we are doing. I feel like there's a piece missing. Because when we call proc A entry, like we are not switching the active stack pointer to anything, to something else, right? Although that should be fine because the stack pointer, okay, so what happens is that this stack here is going to be, this is going to be, yes, the main kernel stack, but it's going to be a function frame where we put some data in there and then we change. And then we set SP as prev SP. So yeah, so we are in our normal stack. It is, I think it is okay for the stack pointer to be in the kernel memory because we are doing this stuff in the kernel memory. We are saving these values in the kernel memory initially. Then we are swapping into our stack pointer now the process specific stack. Yeah, I would like to be able to debug this and watch it run like instruction per instruction. That is so annoying. Let's see if I'm forgetting anything like big in terms of initialization and stuff. I don't think you're getting past the first store word in the context switch function. I see. So you're saying that that's where the exception happens. But it's also weird though that we freeze after that. Yeah, because things go wrong. Okay, so you might be right because to be fair, we only see up to the printing and then we don't see anything else. But what I don't get is if our program counter is inside the exception handler. Oh, you know what? Wait, can we see one of the exception thingies that can tell us what type of exception we're looking at? Because I think that should be set, right? Where do you see, yeah, the S codes and stuff? S codes, Estival, S codes. There we go. 007. Is that invalid instruction? I think we actually saw that. No, it's probably invalid memory access. Oh, I bet you that it's done in here. Did I try to trigger a page fault? Sorry, I'm going forward, but I promise I'm gonna go back to normality soon. Appendix debugging, infomem, scodes. Oh, the exception reason in scodes corresponds to instruction page fault. Right. So no, right. We don't even have virtual memory. Can be a page fault. So what's cause 7? What? Store AMO access fault. I don't know what AMO means for, but that kind of means that you're probably right, Robin. Um, I guess we can do this. What's it called? What was it? An imp? An imp. Okay, let's watch. Let's watch that crash. Okay, unexpected trap. Kernel panic because of an imp. So that one works. So these guys are kind of working. We don't hit the imp. We hit the imp. We hit the imp. We don't hit the imp. So the load causes stuff to go south. Mm, okay, so why is b.sp bad then? Oh my god, did they do the dumbest fucking thing ever? No, I cannot have done that. Okay, I was wondering if I did like initialized PA twice and left PB undefined. But no, we do call create process for PB. I still think that initialization of the SP in process is wrong. You think so? I mean, the original code before I changed it was like this. So let's see. Could there be any trouble? Could there be any problem here? I think this is fine. Like this is pointer casting the pointer to our array as a pointer to U sizes, and then it's slicing it with the number of U sizes that are there. So this should be fine. I expect this to be correct. The sus part is here. That's fair. So we are basically, instead of initializing downwards, we're initializing upwards, right? We're offsetting down and then going back up. So we're saying that at minus 13, if it was minus 1, it would be the last one. With minus 13, we're saying that there's going to be 12 more. Are we not saying that? You know what? Let's do it in another way. Let's do it in another way. Instead of grabbing one element, let's create a subslice. And then we do SP0 is this. And then let's do SP for SP. Can we print out PA.sp and PB.sp after they are initialized and before they're used? Yes. Yeah, I also think that the clearing is not necessary. But I think it can help us catch stuff. Type pointer const slice u size. Oh my god, what monster have I created? Okay, type u size found u size. Yeah. Expected u size found u size. Come on, man. Oh, right. There's a 0 there now. Right, because this is sp1 dot dot. We don't want to override sp0. Sp0 is special case. One 7c. One 7c. Okay, so yeah, should be equivalent. But let's take a look at this stuff. So yeah, let's try to print out pa.sp and pb.sp after they're initialized before they're used. I also suspect that these are pointers, so we want to do this, I think. Eight zero two zero 3229. So let me think about it. Well, this array is in global memory, right? So I guess we should have maybe a definition for procs. Maybe this is okay. What tool can I use to get this information? I guess it's an M, maybe. Grab, I don't know, procs. Kernel.procs is at this address. 8020 8020 3229 1254. Yeah, I think that's reasonable. Man, okay. So pipe less. Oh, it doesn't say much more than that, huh? It just says that this is where the procs array is. Yeah, so it should be there. It should be there. Like the number is reasonable. Or rather, the number points at a place somewhere inside a stack. So that is correct. How many things are zeroing? S0 to S11. Oh, you know what? Yeah, I think I'm doing the math wrong here though. Like I'm placing too much. I'm placing stuff in the wrong place, I think. The SP is odd. I didn't think that was allowed on RISC-V. I think that's fine because that SP value, which, well, it's the value that we write in the struct, right? Is this value. And this value points somewhere inside here. So that is fine. If it ends with a 9, maybe suspicious, but no, it's base 16, so that's also fine. Um, but I'm definitely doing the math wrong here. Because look, this is zeroing 11 things. Oh no, actually 12 things. No, never mind. I'm not doing the math wrong. This is zeroing 12 things, which is actually what's happening in here. So that is correct. Wait, okay, so I was looking at A.sp, and that one is fine. B.sp is this guy. It is kind of a lot. Okay, what's the size of one of these structs? Expected comma after field. What? Oh, console log. 8,204. Okay. So Python, this plus 8,204. Okay, it means that this is between any number, any value between these two numbers belongs, it's part of the of process A. And the second one has to be above that number. So the first one, the first number has to be between this and this. The second one has to be above this. Oh fucking now I broke it. So first number is definitely between these two. Oh, you're right. How do you do this? Right. Thank you. Okay, so between this and this, and it seems it is the other one. Oh yeah, right. Also the other one. Oh my god. No, this is not helping. God damn it. Oh wait, it doesn't matter, right? Wait a second. No, it does matter because this one okay, what is it? Hex? I don't know how to use Python anymore. Can somebody help? So the one to the left is a hex number. The one to the right is not, right? It's base 10. Like, how do I turn this other one in hex then? Data encodings, no. Hex. What does hex do? An integer to the store reporting as a decimal number in string form and returns it. Oh my god. Okay, you know what? Okay, fine. $200C. Wait, this is base 16, right? Yeah, it is base 16. Oh, come on. Okay. 3260. God, thank you. Below 3260. And then it's just right below it, which is correct. The second one is pretty far away from that though. Let's add another 200C. 526C. 526C right below. Okay, so now these values are reasonable. These values seem definitely reasonable to me. Oh, wait a second. Wait a second. Are we fucking inlining that function? That function is getting inlined. I think that's bad. I think that inlining that function is a bad idea. Yeah, I think that what's going on is that we're just like this is getting inlined, and that should not happen. Actually, you know what? I'm actually not sure how bad inlining is, but that's definitely not according to the original plan. I don't remember how you do no inline. Where are you supposed to put no inline? The alignment of the just before the FN. I was getting. Oh, you know what? Maybe it's just my thing that it's dumb. Yeah, no, it doesn't like it. Why did it export? Good point. Okay, we still have the same behavior. Let me look at the disassemble. Now it's calling context switch. Yeah, no inline export function was giving me trouble also. I think this might be something that has been fixed in 0.14 that hasn't been fixed yet in 0.13. Okay, so we still have the same situation, but at the very least, we are we're jumping into the function. Which I think it's good, but we still have Borg logic that hasn't changed. Let's see, but the alignment of the stack field should be to U size 4, and the value you have is odd. Yeah, but it's hex, right? Like if we take that value and we turn it into a binary number, sorry, a base 10 number. Never fucking mind. Okay, I think I understand the problem. Okay, I fully understand the problem. Robin, you were right. Here's what's going on. I'm not making this is a Zig struct. This is not a C struct. So fields and stuff are getting moved around, and there might be extra padding. The enum also is weird and stuff. So what's happening is that this array is not nicely aligned in memory, probably. And that's why we're getting weird odd values. So let me see if I can make this aligned right. Okay, still pooping ourselves, but the numbers are nice now. That's a multiple of 4, I think. So that's a good point. Did the original one do anything in that regard? Or is this something that we kind of like lost in translation? Yeah, it didn't do anything special about it. The difference is that they don't have a weird enum for the state, but they have an int. I guess maybe. Okay, so saying that this needs to be aligned uh, helps. The same should apply also to processes, right? In general, I think. Although these should be inherited, I think. Right? Yeah, for this to be aligned for this also will inherit the alignment. I used to build a microblog and it worked perfectly. Good on you. I know that there's a lot of things in Zine that I still need to improve that I haven't worked on. So sorry, I'll get back to it for sure. It's just that I'm like context switching. I'm multitasking to other stuff. Yeah, process will be aligned for already. Yeah, yeah. So this is good. So we solved one potential issue. This seems fine. Just to double check, here's what we can do. I guess we can take this number. So it does divide by 4. So that's not the problem anymore. I guess the question is, do we still die here? It seems that we do still die there. Yeah, we still die there. Let's look at the machine code for this thing. Context. Oh, is it because it's not extern anymore? It's because it's not extern anymore. Uh, Hmm. Out of curiosity, what happens if we do this? This still has trouble, okay. And if we look at it, this still is fine. Uh, so this function still doesn't do anything weird. But we still have the problem. It's also another thing that I find interesting is that we die also while trying to handle that. Uh, we die when we try to handle the exception, probably because our stack pointer is all over the place. Yeah. Yeah. Let me look at that value. Hmm. You know what? We don't even need 8K, right? I guess we can lower the size of this stuff momentarily as we try things out. I don't think I'm hard coding this number anywhere. So let's make it smaller. I don't know. 256. Did I not save? Oh no, I did not save. So these are the 4 bytes. Uh yeah, these are the 4 bytes. They contain the 2 different program counters. And we tested earlier, the program counters look legit. Everything else is zeroed, so that's fine. Then what else? What else do we want to see? Yeah, let's retrace what happens. We hold context switch. Context switch saves stuff in our current stack pointer, which the first time is not going to be any of these stacks. It's going to be still the kernel stack. Then we set I don't know. Could it be that it's because we are using a global variable and there's something wrong with our global variable? Yeah, because the moment where we fail hard, the moment where we fail hard is when we try to set our stack pointer to a location in global memory. That is the sus thing that we're doing. Let me see if I miss something related to maybe the linker script or something. Save callee, save registers onto the current process stack. Also, it says the current process, but the first time we invoke switch context is not going to be like this, right? The first time we call this, it's like the problem is that the first time we call this, the stack pointer is going to be something else. Scheduler. Okay, before we get into this, I think the core of the problem. Well, I don't know if it's the core of the problem, but definitely one thing is that we're originally calling proc A entry. Like what I'm almost thinking is that instead of calling proc A entry, maybe what we should do is set the stack pointer, change the stack pointer, and jump in here. No. Like out of curiosity. What do we call this? I don't know. Let's just call it S, I guess. PAS. Just return after loading up DSP. Oh, because that will expect the program counter value to be at the bottom of the stack. You're thinking x86. Okay. Call is going to do stuff, right? Move A0SP. Also, wait, why is it load word? Wait a second, wait a second. I think the problem is in here. Okay, you know what I think that it's going on? What I think is going on is that there is some type fuckery in the C code, some type erasure fuckery. And I think the pointer in direction that we see here is not is doing something weird, right? Because this is the dereferencing. This is dereferencing the pointer and placing that in here. I think that what's happening is that we're setting the stack pointer. We're setting the stack pointer to the dereferenced value. I think that's what's happening. Which is not what we want to do. Yeah. This is passing the pointer to SP. It's not passing SP. Oh my god. Why are we even doing this? Where are we? Oh my fucking god. That was it all along, I think. But why are we not passing these things by value? Why are we passing them by pointer? Okay, so let's remove this weirdo shit that I was doing here. Too few operands for instruction. Because it's a mov in that case. Oh no. Wait. I think it's because of the store. Okay. I think we found the problem. And the problem was weird pointer fuckery. Okay, let's see if we can make let's see if we can make our types more expressive than the C ones. I mean, it is what it is. Like that's what it is. That's exactly what it is. Yeah, look, we made some progress. God fucking damn it. Okay, let's restore some stuff. So this make a speech just use size. I could, but at the same time, that's what it does. I mean, SP points always. I get it that it's also just the header is like, you know what? It's fine. Let's keep it. Let's leave it as is. Did I fix both calls? Let's remove some of this printing here. So we got A, B, but then B gets stuck. So the content switch code works once, but it doesn't work the second time. So I guess we want to do this. I guess we want to see what the situation looks like in B, basically. A.sb at you size and then it dies. Okay, I think that now we might be getting into. I don't know what we might be getting ourselves into at this point. I think that now we are observing the fact that A wasn't using its original stack. I think that now we are observing the problem that I was thinking of earlier. The one where the first time that we invoke this stuff, like us entering in the first process, doesn't make us set the stack there. It's a different stack now. I feel like that this part in the book is janky. Let's try to do the thing where we call process asm. I guess we can even make it a move. Am I calling process A and process B with the right things? Yes. You put a comma in there? No, you put it afterwards, right? That's P A dot MV. Unknown operand. Oh. Okay, we're basically okay, we get to the same point though. Even with this system, we do get to the same problem. So it means that there is something wrong in the way we save things or something. Well, maybe we can see. I guess it would be nice to see what the situation is, or I guess was before triggering an exception. Also, the fact that it thinks that A.sp is completely borked, that is not good. Like, I'm really confused about this. Why does it crash at this point? What's the S code? 1. Instruction access fault. Instruction access fault. Yeah, I'm getting a little bit stuck here. Uh okay, so that means that we run through contract switch once and everything happens successfully. But the second time it doesn't work. You know what? Let's run through all the fishy things that we wanted to fix. So let's make it no inline. The answer is there. Somehow I doubt that it's there. So you're dereferencing a null point. Hmm. Yeah, we can uncomment that. Maybe let's not print stacks. Maybe that's a little bit too much. At least for a first run. Yeah, these numbers seem fine. I think they're still also the same ones. They haven't changed. The fact that in B, printing pa.sp is an instant crash seems insane to me. It seems insane because PA is like, yes, PA is a pointer. You know what? I guess we can go step by step. Let's start by printing PA and PB. Carry the process at. Why can't it, like, it's having trouble just straight up printing the contents of that variable? That is weird, isn't it? This should not be causing all this trouble. Or you know what? Wait. You know what? Maybe could be. Maybe what's happening is that we are consuming. We don't have enough stack. Maybe the problem is that we need more stack because at this point, while we're in here, right? The current stack that we're using, it's this guy, and we're using this stack, and we're calling print, and print is kind of complicated. The problem is that even if I do this, we're still doing the thing where the worst part I think is that oh no, right, because we're decrementing SP, right? So anything below is what we're using. Okay, let's go from 8K to 16K something. Yeah, it does not seem to make much of a difference. But I'm correct, right, in saying this that we're writing stuff above the stack pointer, but the stack pointer gets used going down. If PB stack overflows, right? So yeah, underflows, it will override PA's stack. Yes, it will. And PB's process data. Yes. But that still doesn't fully answer why it dies even trying to print simple stuff. The interesting thing is also that it does successfully print up to a point, and then it dies the moment we try to access the value of PA. Hello, Matt. Hello, hello. The fact that it dies at trying to print PA is sus as fuck. So I'm like, I've been doing stuff for 5 minutes without Jacob Lee, and things have not going as smoothly as they did before. We're having some kind of sus behavior. Although you know what, probably one thing that we should do, it's this, like it's really understand what the S cause means. Also, this is 02. Is that the same as before? What the fuck? No, now it's a different one. Wait, illegal instruction. Illegal instruction? Where's the thing that tells me which instruction is the faulty one? Because I think we're making maybe some progress. Sepsi. Okay. 2F0. What am I looking at? Not an M. In kernel entry. Wait. Oh no, I think what's happening is that we're pooping ourselves. I think we're pooping ourselves as we are trying to handle this condition. Maybe we should disable our, you know what, let's disable our exception handler because it's hurting us more than helping us, honestly. Okay, what's going on here? Okay, yeah, I think that thing was like masking the real trouble, the real problems. Uh okay, now SCOs is one. Okay, do you have like a we don't have sub C, but we have map C. Is map C what we want now? I think it's map C what we want. Yeah, but I'm not sure. So you're saying that we try to run an instruction 0. You know what? That might be it actually though. Yes, what's happening is that we are basically loading a 0 as the program counter. That still does not explain though why this is happening as we're trying to print shit. Because the problem is we're trying to print stuff. Like it doesn't happen as we're messing around with assembly, like on our own. It's happening as we're trying to print. I don't think this is gonna make it any better, but like, what happens if we don't even try to print this stuff here at all, and we just print B? I don't know. Uh, so here's what I want to do now. I want to probably, so we should probably not more. This computer is like too powerful. Oh, come on. Okay, so we're flipping around nicely. Uh, so yeah, we're multitasking, I guess. So we're ping ponging nicely. But I'm still weirded out by this. Oh, now it works. I bet you that it was really a stack problem then. Yeah, what I'm thinking is that it was really a stack problem because the only thing that I suspect is that this function is probably kind of stack hungry. Also, which release method are we, which build mode are we building in? Release small. No, in release small, then it shouldn't be too bloated. Okay, I have no clue about of what's going on. Small code, no small stack. Yeah, but I would assume that I was looking at it for. I was thinking originally that it was debug, maybe, where in debug there would be probably a bunch of different function calls, no inlining going on anywhere, and so that would probably potentially eat a ton of stack. But yeah, that's not the case. So, so yeah, I have no idea what's going on. I have no idea what happened. Also, that previously wasn't really working. Now it is working. You know what? Fine, I'll take it. In any case, now we have this. Okay, we successfully implemented another piece of the puzzle. Ooh, let's do also the starting process stuff, which I didn't do. Yeah, starting process A, starting process B. Okay. Okay, scheduler. In a previous experiment, we directly called the switch statement function to specify the next process to execute. However, this method becomes complicated when determining which process to switch to next, as the number of processes increases. To solve this issue, let's implement a scheduler, a kernel program which decides the next process. The following yield function is the implementation of the scheduler. Tip: the word yield is often used as the name for an API which allows you to giving up the CPU to another process voluntarily. Yeah, so current proc, idle proc. Okay, it's like kind of the same thing, slightly more abstracted. Search for a runnable process. If there is no runnable process other than the current one, return and continue processing. Context switch. Can you shrink the stack back to prove the point? Yeah, I can try. By the way, you know why? I think that the weird stack utilization pattern that we were seeing earlier was left in the previous exercise because then it gets solved, I think, by the yield. Does it though? Nah, not exactly. Still weird how they do things. Still working, but we were also printing. We were also trying to print more stuff in here, which might have been the problem. I'm not sure. And even if we make these, I don't know, 1K, very small, still good enough. We need to add ZigX for Prime to choose Zig since he wants to meta program return H1 hello. I think the Primeagen should have all the metaprogramming fun that he wants with Jai, and so that he scratches that itch ideally, and then when he comes back to Zig, hopefully he will have had enough experience to appreciate the fact that metaprogramming is great, but it's also a double-edged sword. I mean, I'm sure that he already appreciates that concept at least to some degree. But specifically, I think that Jai was sold to him as, a better implementation of metaprogramming than Zig. While I would say those words are, I would not agree with that statement, because the reality is that all the limitations that Zig has in comp time, they have been put there for good reason. Like, it's not like Zig's comp time is less powerful because, oh no, we couldn't implement, nobody could design it as powerful as Jai's. I would actually argue that probably Jai's metaprogramming is easier to implement than what Zig has. The problem, the thing is that Zig has comp time with sandboxing for plenty of good reasons, from the ones where like Rust has proc macros that access databases, which is, in my opinion, cool, very cool. Not good though, problematic, because it makes, like, you don't want your compilation process to depend on having a running SQL server on your system or one somewhere in the network or something. It's weird. But also because Zig properly separates things that should be part of the build process versus things that should be done in comp time. And Jai purposely blends the two things. And in my opinion, it's one of those like galaxy brain approaches that Jai has that ultimately do more bad than good. Okay, so long story short, we don't know exactly what happened. We don't know exactly why it was pooping itself when printing, and now it's not pooping itself anymore. Let me try to do. I remember the one problem was with int from pointer. Although this is literally just a typecast, and it shouldn't have any bearing on the generated machine code, but we do change this, and by changing this, we are doing something different in the formatting code. Oh my god. Okay. No, it works. I'm sorry. I guess I can undo a bunch. Yeah, okay. So by undoing, I can repro the crash. But you know what? It seems entirely tied, I think, to these guys. Oh. Yeah, you know what's going on maybe? Maybe what's going on is that these guys are big. I think what's going on is that these guys are big. And while we are on the kernel stack, we can fit these values on the stack in the metaprogramming code that does the printing of these values. But then we can't once we switch to the smaller stack. So let me redo everything. And let me try to print the stack in its entirety again and watch that be the problem. And probably the fact that we were fading earlier has to do with how this stuff gets generated. Yeah, look at this. This has to do with how the metaprogramming, how the comp time generates the functions inside of FMT. So the formatting stuff. It's entirely the formatting stuff. Yeah, and it was succeeding originally. No, print is not buffered, but there's metaprogramming going on, and these things stack. It's a value. It's a big beefy value. So what I suspect is that the machine code generated is basically moving around these things as values and maybe copying them around, etc. Here's a way of fixing it, maybe. Now it's fixed because I'm moving around slices. The code gen from the auto formatter stuff is not great a lot of the time, and it's a bit foot gunny. And normally you don't care, but I think now we're just feeling the effect of the fact that we have super tiny. Not only we have super tiny stacks. That's also the other problem, right? Not only we have super tiny stacks, but our super tiny stacks, whatever the size we set, that's going to be the size of the values that we try to push on the stack. And so it's basically guaranteed to always fail no matter the size. Okay, mystery solved, I would say. Let's implement yield, but I'm still weirded out a little bit. I'm still weirded out a little bit by the fact that they make you call process A, and they don't start by switching to that stack first. That really weirds me out. I came across this when calling an inline function with a pointer to a very large object. Unfortunately, the compiler at the moment moves that very large object onto the stack and then crashes. Yeah. Okay, but again, book is still weirding me out about this stuff. I don't get it. If you try to call it with process A after fix, oh yeah, sure. And I can tell you what's going to happen. It is going to work. It's going to do funky stuff with the memory management, but it is going to work. Basically, what's going on is that, like on the first round that this happens, like the first call, the one that is not initiated by a context switch, but the one that we hard code this, at this moment, currently, our stack pointer is the main kernel stack. It's not this. Where is it? It's not this. So it works. It just moves stuff in, I don't know, in ways that I'm describing as weird because I don't understand why. Like it breaks symmetry. But it works. Okay, so this other version just does yield, idle proc, creates a process, and passes null to it. Idle proc PAD -1, and then yields. The key point of this initialization process is current proc equals idle proc. This ensures that the execution context of the boot process is saved. Okay, so that's where the weird stuff was happening. So yes, it does break symmetry, but there's a problem with our solution, right? Doing this, doing the asm volatile stuff that I was doing, that works. The problem is that if we do this, we lose completely the context of our main kernel process. It's not a process in the sense of our reified process, but it is a, let's call it, thread of execution, and we lose that information and we never restore it. But at the same time, it's not like we have a way of returning from our processes, so once we get into those, we keep ping-ponging forever. So what they're doing now is that they're creating an idle proc, and basically the idle proc then gets executed again. This information gets saved inside idle proc. Let's see what it says then. During the first call to the yield function, it switches from the idle process to process A. And then switching back to the idle process, it behaves as if returning from this yield function call. Yes. Panic. Switch to idle process. Last, modify a proc entry and proc b entry as follows to call the yield function. If A and B as printed as before, it works perfectly. We need to update it slightly. I think that we were experiencing that earlier ourselves, like the fact that our exception handler wasn't really helping and pooping itself. It's because it was implicitly depending on the shenanigans that we were doing. So first, set the initial value of the kernel stack for the currently executing process in the S scratch register during process switching. Set the initial value of the kernel stack for the currently executing process in the S scratch register. Hey, Mr. Gecko. Well, if you go on GitHub, you can find a VOD of what I did yesterday. This is just my second day working on this. So the first day, there's going to be a lot of smooth progress, and you can watch that VOD if you're interested. Or not, and just do stuff on your own. Although there are some gotchas that I had help with. So be mindful of that. So let's see. Since the stack pointer extends towards lower addresses, we set the address at size of next stack th byte as the initial value of the kernel stack. The modifications to the exception handler are as follows. Retrieve the kernel stack of the current process from S scratch. But why are we doing this every time we yield? Can you not just do that like once? I guess it's because... No, you can't do that once, because if your plan is also to occasionally execute back the main kernel function, that one could get into another function, like could call another function, and deeper in that function, it could yield. And so you want to do that. But I'm not sure I understand something though. Okay, you know what? I'm going too deep. I need to actually implement this stuff so that we can go step by step. So let's go and implement more of this stuff. Okay, so now we want to implement yield. So we still have switch context, but we want to implement yield, and I don't think we need to have process A and process B anymore. Oh no, we do have proc A and proc B as globals. Interesting. But I don't think we actually need them. So let me nuke them as globals. Const VA, const BB. Oh. Then we need to implement create process, process A, process B, context switch. Let's put it above context switch. Okay, we have yield. Finds search for a runnable process. Struct process pointer next. Idle proc. So it tries to find one that is runnable and with a PID greater than 0. Interesting. Okay. So next is going to be for procs if p dot state is runnable and PID is greater than 0, break. Else, what do you do with else? If there's no runnable process other than the current one, return and continue processing. Okay, else return. We do have next. Current proc becomes next. And then we switch context. Okay. Current proc, idle proc. So current proc is next. And then switch context. Prev. Right? Right. So this seems to have been implemented correctly. We are assigning PIDs wrong because we need to do +1, I think. I +1, so that they are never 0 when we create a process, I think. No, or we can start, I think, at 0. We just need to make sure that the first process that we create is the idle process. Yeah, they're doing the -1 thing. I'm not going to do the -1 thing. I'm going to use 0 as my sentinel value. Okay, so we have the idle process. Idle process is going to have ID 0, I believe. Yes. And then we consider PD has to be greater than 0 for it to be considered a candidate. So this is good. Context switch. And then we set current process to idle. Okay. So we do this. Your logic is different from the C code. In the C code, it would else from the 4 with idle process. Oh, does it? Oh, you're right. It defaults to idle process. Yeah, thank you. Good point. That actually makes more sense than what I was going for. So let's look at where it's yield. So idle proc is all, it's the idle process. I guess it's like this then. Yeah, we default to the idle process. And then the exit condition is a different one. The exit condition is it's this. Okay. So we have, I think, pretty much everything, right? At this point. We're missing yielding from main. And I think at this point, this is not needed anymore, I think. And now I have to fix the fact that we can't call context switch directly anymore. We need to call yield. We can't print all these diagnostics stuff anymore. So let's revert these prints to something simpler. Okay, so we're yielding. There's a panic. Switch to idle process. Okay, let's panic. Pointer capture of non-pointer type kernel process. Oh, yeah, again. This is doing a lot of A, not a lot of B. Wait, am I did update this thing. What the heck? Wait. It's because I need to set them to running, right? I'm not setting them to running. I need to exclude them. Wait, is this really not covered in here at all? Okay, let's see. Testing context switch. This is the previous version. Scheduler. Hey, Crimson Mana. Holy shit. Thank you for the gifted tier 1 subs. Okay. Thank you very much. Wow. Well, as you can see, Bork is not designed to expect this kind of stuff. Thank you very much. So yeah, I'm basically I'm trying to find the first runnable that has PID greater than 0. I think we need to keep track of basically what it is that we're running, right? Well, enjoy the subs, everybody. I don't know. Make sure to renew them. So let's make yield update the state of these processes. So I'm not happy that I'm straying away from the book, but because it's probably that I'm missing what they're trying to make me do. It's not worked. It worked, but yeah, it's not optimal. The Primagen probably can't use Borg. Borg would have to be redesigned slightly for it to work for the Primagen. I mean, it could totally pull it off performance-wise, but yeah, this stuff, that's like his chat would be unreadable, I guess, at that point. So process is unused, runnable, and running. Yeah, wait a second. No, that wait a second. This is still not convincing me that this is why we are observing this. So we call yield the first time, and we try to find a runnable process, and we do find it. It's going to be process A, and so we're happy. Then we call yield from process A. I think I'm not implementing this stuff correctly. Because this should avoid, this should skip the current process, right? Like one that is current, the one that is running. I think the key is in here. It's looking. Oh, I see what it's doing. It's saying it's looking only at processes after the current process, and then it's doing modulo. Jesus Christ. Okay, so the fact, okay, I understand the value of doing some of this work. Okay, the point of the modulo is that, well, without the modulo, if you straight up don't have the modulo, then you're going to go out of bounds, because basically you're creating, like, you're going to try to index. Let's say that you were running the last process, then you do +1 and you go out of bounds, and that's bad. With the modulo, you basically wrap around back to 0. So yeah, let's implement that. So that means that the search is not from all of procs, but it's from procs starting from the current process ID onwards. +1 onwards. The problem is that we're not doing the modulo thing with this syntax yet, so we do it here. You know what? I feel like that this should be like this. There you go. Starting process B, kernel panic switch to idle process. Okay. Is it the +1 the problem? Current is going to have address 0. Yeah, and by the way, this is also working on another assumption that the PID reflects the index basically in the array. Okay, I think we're having like a silly off by 1 error. We fix this and then we're happy. So initially current proc PID is 0. Oh, that's maybe where the -1 comes into play. So yeah, that's when the -1 comes into play, isn't it? But it still should be fine. So first, initially the current process is the idle process. The idle process has a PID 0. So we say that we start from 1 modulo proc len, which is going to be 8. So it's 1. And so we do starting from the first index. So we skip the idle process and we go to procs 1. And that should give us the that should totally give us the process A. And then we should context switch into it. So this in my mind works. Oh, wait. Wait a second. Okay. Wait. You know what? Maybe actually this was working and I didn't realize that. Yeah, I got weirded out by the fact that it was saying B, but no. It says starting process A. It does A. That's correct. Then it does B, but then it switches to the idle process. Now, I guess the question is this correct? Why are we switching to the idle process actually? Okay, let's add some, you know what? Let's add some debug printing here. You found A, then next year you found B, and then the next year you loop to the end of procs and find no other processes. You are skipping look at 0 to start IDX. Yes, you're right. I find B. B is lower than procs. How does the original one deal with that then? Oh, because they loop multiple times. Else for. Oh my god. Do we do the else for? I guess. That seems horrible though. What would be a neat way of expressing this? I would say maybe more than a else for, it's like a nested for. Either else for or copy more verbatim. Yeah. Okay, else for it is. Oh my god. Error union is ignored. Oh, it's the extra printing that I was doing. Yeah, we can get rid of it. Okay. So we're ping-ponging correctly. Okay, changes in the exception handler. Now, this part I didn't fully understand yet. So I understand the general problem. I don't understand how the solution is correct. Man, by the way, the love for like sneaking weirdo like nuanced behavior into like super concise stuff, I don't know. I'm not a fan of these. Like I understand the fact that if you're proficient, it's nice to be able to express things concisely, but man, unpacking and digesting this stuff is hard. And I get it that if you're a C programmer, then you get used to these patterns and you recognize them more easily, but I don't know. I personally appreciate the less hermetic approach that Zig has to complex algorithms. That said, I get that that's a personal preference. The only way to get down to 1,000 lines, it does play a role. That's for sure. Yeah, and to be fair, it's not like this is a work of art, right? This is ugly. So maybe it turns out that that implementation is actually the most like reasonable one to have. So yeah. But then at the same time, I'm not sure it even matters because this is obviously a simplistic scheduler. Like a real scheduler would have a different, a more nuanced algorithm for prioritization. So like this is cute and all, but that's not the real thing anyway. So in any case, okay, let's fix our exception handler. So in the exception handler, it saves the execution state onto the stack. However, since we are now using separate kernel stacks for each process, we need to update it slightly. First, set the initial value of the kernel stack for the currently executing process in the S scratch register during process switching. Like this is writing. Okay, this is looking at the next it's looking at the next process, the one that we have found and plan to schedule now to switch into now. Looks at the stack, size of next stack. So this is grabbing a pointer to the very end of the stack. CSRW is writing that value in S scratch. Why are we writing down the end of the stack? Well, or I don't know what to call it, the beginning, like the very top. Since the stack pointer extends towards lower addresses, yes, we set the address at the very top as the initial value of the kernel stack. The modifications to the exception handler are as follows. Read write. Retrieve the kernel stack for the running process from S scratch. CSR read write. I don't understand how CSR read write works. It's like read. I guess it's read S scratch into SP and write SP into a scratch. What? Retrieve and save the SP at the time of the exception. Reset the kernel stack. The first CSRW instruction is a swap operation. In short, put SP in a temporary variable, set SP to S scratch, and set S scratch to the temporary variable. Thus, SP now points to the kernel, not user stack, of the currently running process. Also, S scratch now holds the original value of SP, the user stack, at the time of the exception. After saving out the register onto the stack, we restore the original SP value from S scratch and save it into the kernel stack, and then calculate the initial value of S scratch and restore it. The key point here is that each process has its own independent kernel stack. By switching the contents of S scratch during context switching, we can resume the execution of the process from the point where it was interrupted as if nothing had happened. which I guess is going to be important for syscalls. Tip, we've implemented the context switching mechanism for the kernel stack. The stack used by applications, so-called user stack, will be allocated separately from the kernel stack. This will be implemented in later chapters. Okay. Well, let's go implement this, I guess. Okay, so as volatile, CSR right. Now we want the end. How do we do the end? Also, this this needs to happen after we found next. So we're saying we're gonna put it here. Yeah. Can you access the enum tag field of a tagged union variable? Yes. I.e. my union.tag or type enum. Yes, you can. It's not that simple, but look at std.meta. So look at learn, standard library documentation, active tag. So active tag returns the active tag of a tagged union. I'm sorry. I'm assuming that that's what you want. Actually, looking better at your question, you might have wanted something else. But I think most of the time people want this. And if it's not this that you want, look at the implementation of this function, and it will give you an idea on how to access the tag type. The point though is that there is no tag field. It's not abstract. So the tag information, the tag is in there. It's just not accessible as a dot something, because dot something gives you access, well, to the active thing, right? So yeah, I'm assuming that that's what you want in any case, active tag. You should be happy with that. Okay, top of the current of the stack of next. So that would be I guess that would be pointer of next dot stack at stack dot len -1. And that's it. Okay, then in kernel entry, we might want, I guess, to re-enable this guy then. Y -1, that's not what the C code does. Let me think about it for a moment. You're right. They are indexing out of bounds. The problem is that I can't index out of bounds, right? I guess I can do it like this. I guess I can do it like this. There you go. You can hit the address of an out of bounds index. Really? I know that I can do it this way. Like you can access the pointer field. That gives you a point. I didn't think about it in the beginning. I thought about it once you pointed out that my thing was different. And from pointer, you can slice it however you want because you're not bound to the mechanics of the slice. I'm surprised that you can take the address of an out of bounds index. The index actually, I would expect that to still trigger a panic in debug and release safe. The UB is on read or write. Yeah, well, I agree on the fact that it's not UB, but you know, Zig can give you. I think Zig could panic, maybe should panic. I don't know, but it seems to me that it should panic even if that is not immediately UB. So the modifications to the exception handler are as follows. I'm gonna just copy paste this. Retrieve and save the SP at the time of exception. You know what? I'm just gonna copy everything and then adapt it afterwards. This is where in kernel entry. Oh god, was I doing this stuff in the wrong place? Kernel entry. Yeah. What are we looking at then? Before move A0. Okay. Okay, let's see. I'll leave it there. Okay, retrieve and save the stack pointer at the time of the exception. And then store word there past the end. No member name PTR. Oh, shit. Right, it's an array. Right, if that was a slice, that would have been easier. I guess I can do it like this. Are we going to be getting a new Z conference convention with Dev Talks in Milan this year in 2025? Probably yes. I'm not sure about the details because I haven't started working on it, and there's a bunch of annoying blockers. And until those are solved, I'm not going to start working on it. And so, I'm sorry. I can't make promises. Okay, so it would be nice if we could like test this stuff out. Let's see, appendix. Why do we reset the stack pointer? In the previous section, you might have wondered why we need to switch to the kernel stack by tweaking as scratch. This is because we must not trust the stack pointer at the time of the exception. Oh, but did we learn that lesson? We totally did learn that lesson hard ourselves. In the exception handler, we need to consider the following three patterns. An exception occurred in kernel mode. An exception occurred in kernel mode. We're handling another exception, nested exception. An exception occurred in user mode. In case 1, there's generally no problem, even if we don't reset the stack pointer. In case 2, we would override the saved area, but our implementation triggers a kernel panic on nested exceptions, so it's okay. The problem is with case 3. In this case, SP points at the user application stack area. If we implement it to use and so trust the stack pointer as is, it could lead to a vulnerability that crashes the kernel. Let's experiment with this by running the following application after completing all the implementations up to chapter 17 in this book. Oh, come on, man. Let's see. Example of applications, user.h, So this is like a huge foreshadowing that we are not ready. It's like a Metroidvania. It's like we're seeing that this thing, but we can't access it yet. In any case, what is this thing doing? Li load immediate. Load immediate that beef into SP and imp. Okay. So basically, this is corrupting the stack pointer and triggering an exception. If you run this without applying the modifications in this chapter, i.e. restoring the kernel stack from scratch, the kernel hangs without displaying anything, and you will see the following output in QEMU's log. Aborted right to the stack, dead beef. First, an invalid exception, invalid instruction exception occurs with the unimp pseudo instruction transitioning to the kernel strap handler. However, because the stack pointer points to an unmapped address, an exception occurs when trying to save registers, right? Because we in our handler thing in here we do depend on SP. Like we do stuff with SP. We were seeing that. You know what? What's funny is that we didn't even need this. Like we already unlocked this, our own version of this. So yeah, we had already experienced this stuff. Another solution is to have multiple exception handlers. In the RISC-V version of XV6, a famous educational Unix-like OS, there are separate exception handlers for cases 1 and 2, and for case 3. In the former case, it inherits the stack pointer at the time of the exception, and in the latter case, it retrieves a separate kernel stack. The trap handler is switched when entering and exiting the kernel. Yeah, but what if you corrupt your own stack pointer in the kernel yourself because you wrote some wrong code? How about that? That's like an attack vector that this book isn't thinking about. In Fuchsia, an operating system developed by Google, there was a case where an API allowing arbitrary program counter values to be set from the user became a vulnerability. Not trusting input from users, so user applications, is an extremely important habit in kernel development. I mean, yeah. Okay, now we have achieved the ability to run multiple processes concurrently, realizing a multitasking OS. However, as it stands, processes can freely read and write to the kernel's memory space. It's super insecure. In the coming chapters, we'll look at how to safely run applications. In other words, how to isolate kernel and applications. Nice. So we survived also this section. We got processes running. But yes, they are all still running in kernel mode, so they can all mess around with all the memory and do all the stuff. So I guess the next section enables virtual memory. It's going to have us set up page table and everything else. And I guess that's going to be like a necessary step towards being able to have user mode. So what am I going to do now? I guess I'm going to commit maybe my changes, and then I think I'm going to call it a day. It's been a 4-hour long stream. It's been fun. Progress has been slower than, like, yesterday I did all the first 8 sections. Actually, was it 9? No, was it 8? I did the first 8, and today we only were able to do 2, right? Memory allocation and process, 9 and 10. But we did encounter some puzzling problems that we solved, actually. So thank you for the people who helped. Thank you, Robin, a lot. Thank you very much. And yeah, I guess tomorrow we're going to do page table and then application and then user mode and then system call. As I said, I'm not going to do everything. I'm going to skip the file system part. I'm not interested personally, but whoever wants to, they are free to do that too if they want. Also based on the code that I'm now going to put on GitHub. All right. You must be joking, man. Okay. So thank you all. I'm gonna update also the README with the VOD link once I stop streaming. And yeah, I hope everybody had fun. And if you missed the first part, go check out the repository Christ OS on my GitHub, and there you will find also links to the VOD of the first day. Yeah, thank you all, and let's see if I can raid somebody. I don't know. Is anybody doing Zig? So Primagen is doing. I'm not gonna raid Primagen doing Jai. I mean, it's fine. I'm joking. But let me see if there's anybody doing Zig. I should raid people doing Zig. There doesn't seem to be anybody doing Zig, I think. So yeah, I think this is it. I'm gonna call it a day. Thank you all, and I'll see you next.